Okay, good morning everyone. Yes, so before starting our lecture 20, I wanted to check your attendance first. 이재혁 씨, 고하늘 씨, 심준호 씨, 이승빈 씨, 이정태 씨. So if you are here, please leave your message. 네, 이재혁 씨, 안녕하세요. 심준호 씨, 안녕하세요. 이승빈 씨, 안녕하세요. Okay, then let's move to the second page. 이충하 씨, 정상아 씨, 홍주표 씨. 네, 이정태 씨, 안녕하세요. 이충하 씨, 안녕하세요. 정상아 씨, 홍주표 씨, 네, 안녕하세요. Okay, now we are going to the third page. 김민선 씨, 김유신 씨, 배민열 씨, 배서령 씨, 서하연 씨. 네, 김민선 씨 안녕하세요. 배민열 씨도 안녕하세요. 배서령 씨도 안녕하세요. 서하연 씨 안녕하세요. 김유신 씨도 오셨군요. 네, 김민선 씨, 김유신 씨, 배민열 씨. 네, 비자 인터뷰 때문에 저번 시간에 출석 못하신 분들 중에서 한 분이 그 서류를 확인서를 제출을 안 해주신 것 같습니다. 저한테 이메일로 보내주셨으면 좋겠고요. Okay, we are going to the last page. 조대현 씨, 최승규 씨, 그리고 김성수 씨, 미스터 마니퀴에르. 네, 최승규 씨 안녕하세요. 조태현 씨 안녕하세요. 김성수 씨 안녕하세요. Good morning, Mr. Manicure. Okay, so I will check the your attendance at the final trial. 고하늘 씨 그리고 고하늘 씨만 오시면 다 오시는 것 같네요. 네. Okay, so I will check his late attendance. Okay, good morning everyone. So we are already in lecture 20. Wow, time flies. So before starting our lecture 20, I wanted to take your questions, and if you have no questions, then I will move to lecture 20. And announcement about our lecture progress, I mean the type of our lecture. So we are now in fully online lecture today, and lecture 19. It was because there was a COVID-19 positive case, but I hope that in next lecture, lecture 21, this Wednesday, we will come back to our classroom, and I want to try to the offline lecture. So how about 네, 고한우 씨 안녕하세요. So how about your opinion about our fully online lecture and offline lecture? So if you have any feedback, then please send me an email, and I will try to improve my both of online and offline lectures. So that was just an announcement about lecture type. And how about the technical contents? Do you have any difficulty to solve your previous homework 19, or any question on lecture contents is welcome. So also, if you have any question, then you can. Okay, so you are now asking Mr. Kim. You are now asking the explanation about our previous homework number 19, problem 3. So why don't you just discuss about it together? So let's share our experience with all of our students. Okay, then. Yes. So I hope that now you can see my screen, and how can I? Oh, okay. It looks much better to have. Okay, can you see it clearly? Okay. So if we are going to the problem number 3, pointed out by Mr. Kim, so the 17th line and 18th line is corresponding to his question. So calculate the maximum value of dV out over dV in. So in order to understand this problem, first of all, we have to draw this one. Yes, here we have y-axis V out. Actually, this is the drain voltage of our MOSFET. Also, here we have V in. This is the gate voltage of our MOSFET. So now we can think about a square whose for the side length is given by VDD, so you can think that okay, there is a certain square, although it is not perfectly square in my drawing, but you can understand that my intention. So And in the previous lecture, we have discussed about the V out as a function of V in, and yes, there was a certain point. Yes, so when we have zero input voltage, then output was almost exactly zero, and even when we go to the high gate bias voltage, like a VDD, yes, the output voltage can be reduced significantly. So although this is not exactly zero, but there is a certain point we have quite close to zero. So I think that all of you can now understand the discussion. And how about the intermediate state? So intermediate state, so before reaching to the threshold voltage, still our transistor is turned off. So from the viewpoint of our VDD, and it has the connection to our resistor R. However, MOSFET is effectively turned off, so VDD is just copied into our out node. So that was the situation. After that, now our transistor enter into the saturation mode. So we have steep change of our steep reduction of our output voltage. After that, when gate voltage is further increased, then our gate overdrive voltage was VGS minus VTH is continuously increasing, and also our VDD, the drain voltage is continuously reducing. So eventually our transistor enter into the triode mode region. So in this case, yes, our curve now much smoothed or less steeper than this central region. So that was some schematic expression for our V out versus V in graphs. So I think that all of you can now understand this procedure. And the homework number 3, or problem number 3, just to ask you to calculate some quantity like this, the V out over the V in. So everywhere in these graphs, so you can try to calculate something like the slope of this green curve. For example, if we are taking the slope of this green curve, then maybe it is just becoming a horizontal line. So this is the curve corresponding to the derivative. And also when you go to here, somewhere here, then maybe the curve has finite slope. However, its slope is not that steep, so you can easily understand. And only when starting from this saturation mode, slope is becoming steeper and steeper. So what I ask you is not exactly calculating this dV out over dV in, but you have to calculate the negative sign because it has always a negative sign. So I wanted to have the positive sign. So now you can understand this situation. So where will be the point you have the maximum negative slope? So can you imagine? So compared with this point, okay, this one will have a steeper slope because you know that this is just inverted parabolic curve. So always approaching to this part. So when you move into our input voltage, we will have steeper and steeper slope. And let's go to the edge or border between two different curves, so sub curves, so for corresponding to our saturation mode and corresponding to our triode mode. So within this saturation case, this point, we will have the steepest one. After that, when you enter into a saturation mode, then suddenly we have a much less steep curve, because you know that now the transistor equation becomes different. So think that if you try to calculate this maximum point for this negative slope, then you will find that this part, this point, is corresponding to the maximum value of your negative slope. So of course, this is one intuitive way. Other way to solve this problem is just to blindly calculate the derivative as a function of gate voltage. You can do it, and just to make a comparison, then you will find that still this border point or the edge point is corresponding to your maximum negative slope. Okay, so Mr. Kim, so is it enough for your question? So if you have a further question, then please let me know. And also other students, so if you have any question related with this explanation, then of course any of you can ask me questions. Okay, so however, before wrap up my explanation, I wanted to give you one warning about one note about this problem. So if you have successfully done this homework problem, then I am afraid that many of you have some feelings about this one. Okay, so in order to get the maximum negative slope for this V in, V out versus V in curve, we have to try to find out the point where our saturation mode and trial mode meet together. We are now trying to find out this point. However, this is not the case. Please note that up to now we have assumed that this is a constant over wide range of our gate voltage. As I told you before, this mobility can be a function of VGS. So if we usual tendency is once we have turned on device, so when our gate voltage is larger than threshold voltage, then when we apply higher and higher gate bias voltage, then mobility becomes lower and lower. So you know that here we have a really beautiful parabolic curve. However, this parabolic behavior only originated from the constant property of our mobility. Okay, if we have non-constant mobility, then what will happen? If we move our input voltage from here to there, if mobility is constant, then we will have this inverted parabolic curve. However, in reality, since mobility is degraded, its value is reduced, then it does not increase in perfect parabolic curve, and that slope is diminished. So reduced. So the actual point where you have the maximum negative slope is not occurring, actually not occurring that border point, but somewhere in here. So not exactly here and somewhere in here. Then how can you find out this optimal point for maximizing your negative slope? That really depends on your technology. So depending on your manufacturer, your vendor, you have different technologies and different values of VGS, your quantity becomes showing the maximum value. Okay, so then I wanted to ask this one. Then where can we have actual maximum value? It is certain that this curve just simply means that our ID, partial derivative of ID with respect to VG, that is closely related to the maximum point of this slope. You know that here we have a round ID over round VG, and we are now talking about the V out and the V in. You know the V in and VGS, they are identical, and also we have a certain relation between V out and ID. What was it? So V out is simply given by VDD minus R times ID. So change of our drain current is just immediately copied into our V out change. So now you can understand this is simply multiplying minus R. Then that will become equal to dV out over dV in. So now the problem becomes try to find out the point, the gate voltage where we have maximum round ID over round VG. So this quantity now becomes a practical importance. So when we have a point gate voltage where this round ID over round VG is maximized, then we can also achieve the maximized dV out over dV in. Okay, so if we wanted to make a maximum value for dV out over dV in, of course negative sign, then we have to find out the point where we have maximizing this round VD over round VGS. Do you have any questions? So I took a question, or very good question from Mr. Kim. After that, I just added one note about the actual consideration about having the maximum slope. And I'm waiting for other question from you. So that was a really good question and aligned to my lecture progress also. So if you don't have any further question, then please let me move to the next part. Okay. So now it is quite important to find out this quantity. So, so from our previous explanation for our V out over V in, now this quantity is really important. So if we have this quantity maximized, then obviously we can also maximize dV out over dV in. So it has its own name. Since it is so important, so I will try to define this quantity. This quantity has its own name, like transconductance. So let me just explain a little bit more about it. So transconductance, it seems like that sounds quite long and weird, but you can immediately find that that is just a word generated from this prefix trans and conductance. So you know the conductance. What is the conductance? Conductance means that the quantity which is just to show here current divided by certain voltage. So this one, quantities like these are called as conductances. So conductance means that a quantity which is the current divided by voltage. So as you can see here, it's a definition. So it has ID and VGS. ID in the top and VGS in the bottom. So you can find that this is really corresponding to the conductance. However, why do we say it as transconductance? It is only because you know that here we have ID and this is VG. So think about a resistor in contrast to our transconductance. Think about a resistor and there is a negative and positive terminal. Then if I ask you, please try to calculate the resistance, then how do you calculate it? Okay, this is the resistance R. And if I ask you, please calculate the conductance of this resistor, then how do you answer to my question? So conductance is simply given by the inverse of our resistor. So resistor has a physical dimension of ohm. So of course this one conductance have the physical dimension of 1 over ohm, and sometimes this 1 over ohm is called as Siemens. But anyway, so this is a simple way. In this case, we just consider this negative terminal is grounded and we apply certain signal to the positive terminal. So we apply certain voltage excitation to the positive terminal and try to get the response of current corresponding to also positive terminal. Why? Because negative terminal is regarded as a reference terminal. But now think about our MOSFET instead of our resistor. Then now things becomes a little bit more complicated. So think about this MOSFET. Yes, now we have MOSFET and it has at least 3 terminals. Of course it has 4 terminals, but you know the body contact is tied to the source. So now we have a source, of course, gate and drain. Yes, once again source is grounded. After that, we can think about various ways to quantify its conductance. Okay, simple. Take the current and take the voltage and take their partial derivative. However, point is now we have here we have 2 terminals, 2 remaining terminals. Yes, consider the N MOSFET as a 3-terminal device and took the source as a reference. Still, we have 2 different gate terminal and drain terminal. So if I just list out the available quantities corresponding to the conductance, for example, we can try these quantities like Ig over Vg and Ig over Vd and Id over Vg. Finally, Id over round Vt. Okay, you can find 4 different quantities. Why do we have so many quantities? This is because now we have multiple terminals, so each of our current quantity and voltage quantity can have different terminal indices. It can be a current for drain terminal, or it can be a terminal current for gate terminal. Okay, so do you have any question? So up to now, I just explained that conductance is a quantity corresponding to the voltage divided by current divided by voltage. Of course, it is not just a mere division, so we have to think about the partial derivative. But anyway, so in the case of MOSFET, since we have two non-trivial current and voltages, so we can define gate voltage and drain voltage, gate current and drain current. That's the reason why we can define four different quantities. So if you have any question, then please let me know. Then let me just test each of them. So here first we can think about the round Ig over round Vg. Okay, so that is actually quite important quantity. Yes. However, let's just restrict our discussion about low frequency. Low frequency means that we are operating our device in a quite low frequency. In this case, actually, at low frequency, we can assume that gate voltage is equal to 0. So if you attended our previous lectures, then you may have a still question why you introduce that similarity or approximation symbol to this one. So gate current was just to assume to be 0 when we talk about the MOSFET. Yes, when we talk about the DC characteristics, that is certainly sure that we have almost vanishing gate current. However, if we go to non-zero frequency, which is, for example, 1 hertz, 10 hertz, 100 hertz, like this, then yes, gate current is not exactly 0, but its magnitude can be thought as quite small. So, however, this is not that case at a high frequency, but anyway, let's make it simple. So, if we are restrict ourselves to low frequency cases, then since gate current is so small, so quantities related with these two becomes practically not that important. So now we have to consider the quantities related with a drain terminal. Then now we can think about two quantities like round ID over round VG and round ID over round VD. Okay, now we can think about two quantities, and please make the difference between them. Now we have two quantities, ID VG and ID over VD. They look similar, however, their difference comes from the different gate and drain terminals in the lower part. It means that although we are observing the same quantity, the response of drain current, but the reason why we have the response, so the perturbation is different. So we made the excitation, voltage excitation to the gate terminal here, and now we have voltage excitation in drain terminal. Okay, so think about this one. Here, in the case of drain ID over VD, then we have made drain pair of terminals. We introduce a certain excitation in drain and observe it the same terminal. So this is a self calculation. However, when you have a look at this quantity round ID over round VG, this simply means that you have made a certain excitation at the gate terminal and observe its impact at the drain terminal. So they are different. So impact is transferred from gate to drain. So there is a translation of their effect. So that's the reason why this quantity is called as transconductance with the prefix trans. So trans means that simply we have two terminals and the effect is not within the same terminal, but this conductance quantity is related with the interaction between two different terminals. That's the reason why we have transconductance. So now let me just summary my discussion about transconductance. Okay, simply speaking, now when you consider your transistor, so one of a very important quantity is round ID over round VGS. So it just to describe the sensitiveness or sensitivity of your drain current with respect to small change in your gate voltage. If this quantity is small, then your transistor is sensitively increase or decrease the drain current with respect to the change of gate voltage. If this quantity is quite low and close to zero, then although we change gate voltage, drain current does not change. So that is the physical understanding about round VD over round VGS. So this is called transconductance, and we have almost a universal symbol for it. So there is like this GM. Yes, this is small letter G, and here we have this is a subscript. So sometimes in our homework, I will just write down GM or G sub M, but please note that this is all corresponding to this GM transconductance. And yes, that is quite important quantity. And you know, within the course of discussing the importance of GM, we have one accompanying quantity like this, round ID about line VD. So how can you call it? So this is corresponding to, of course, conductance, and this is a self-conductance, obviously. However, instead of this conductance quantity, so instead of that, we just took its negative value. Oh, sorry, not negative value. Sorry about that. So it's inverse. So the previously it was conductance, and if we take the inverse of conductance, then what is it? This is corresponding to a resistance, and this one, this quantity is resistance, and that has its own name for MOSFET, so we call it as output resistance. Why do we call it as output resistance? Because you know that drain terminal is typically called as the output terminal and used as an output terminal. So now you can understand, in order to quantify our MOSFET, here we have three terminals: source, gate, and drain. From this schematic, we can think about two important quantity. Yes, GM and R out, output resistance. Although they are written in their own symbols, but anyway, their physical definition is quite simple. ID over VGS, and this guy is just inverse of round VDS. Yes, that's it. So now you can understand, basically there are two quantities corresponding to different position of voltage excitation. Okay, so I think that I have just covered two important quantities for specifying this transistor. Of course, the reason why only we have two quantities, two important quantities instead of four important quantities, was we made the assumption that Ig can be negligible, and this expression or this assumption is strictly valid only at low frequencies. Please note that if we go to higher and higher frequency, this assumption becomes invalid, and we have to consider also quantities corresponding to Ig versus Vg, or Ig versus Vd. Those quantities becomes also important. Okay. Okay. So, any question from students? So, if you have any question, then please let me know. So, please have your time to think about these two quantities, and if you have any question, then please interrupt me anytime. So, even though when during my explanation about any other lecture content, you can interrupt me. So then I will try to make some time to explain. So yes, now think about this situation. Now you wanted to introduce, or you wanted to build a certain amplifier. Amplifier means that now you have a certain small signal input voltage. So, and by action of an amplifier, you wanted to have V out. Yes, also small signal V out. But what you wanted to have is, okay, you have small voltage, input voltage, and after action of this amplifier, something called the amplifier, then you have although small, but now it becomes a little bit bigger. Okay, so seemingly like this: small signal input, and after that, although small again, but now it becomes bigger. That is the intention of our amplifier. Okay, then yes, here we have small amplitude, and this one becomes a little bit larger. So this is the desired case. So think about this one. If we have a small signal, and after action of our amplifier, so-called, then now we have this waveform. Then is it really good for our amplification or not? Obviously, you know that this one is a failure of amplification. Although we have meaningful signal, but output, the red curve, is just its amplitude is diminished, and yes, we have nothing available for our engineering purpose. So this is bad. The lower diagram shows a bad case, and upper part shows us a good case to be used in our engineering sense. So let me just consider this curve for basic starting point for our amplifier discussion. Yes, then now we assume that we have a certain case of a curve V out versus V in. Now we have this kind of curve, and also we wanted to use this curve for our amplification purpose. So my intention is like this. Since V in can be used for input voltage of this system, what I wanted to do is first take a certain DC voltage. So DC voltage means that if VDD is, for example, 1.8 volt, yes, depending on your choice, your means that a designer's choice, for example, let's say 0.9 or 0.8 or something like that. That is fixed by you, and also introduce small input signal. That is the typical situation we are assuming now. Then think about this one. Let's say this is your VDD and it's 0, and let's just say I just took this point as a V in DC. Yes. So after that, I just introduce my signal in a form of a small voltage excitation V in. So my signal is just added to this V in, and as the time goes, then I will just introduce such a kind of a signal. Yes, so if time is elapsing, then I will just add this kind of a signal. Of course, please note that this vertical axis is not the time axis, but anyway, just to try to understand. In this part, for example, this is a time axis. This is the situation. Then what we wanted to have is, okay, then by action of such a system which have only one N MOSFET and one resistor, we will have also certain waveform. How does it look like? Maybe let's try. Maybe the DC, V in DC will set up the certain output voltage. So V out DC, that will be determined by what? Determined by our V in. You know, here we have V in DC, and this DC input voltage will determine this DC out voltage. Yes, you can understand this one. After that, your added V in will be transferred to what? Your time dependent V out. Then please think about this one. What happens to this point and that point? So let me just magnify our curve like this. Okay, so if you have any question, then please interrupt me. This part is important, so please interrupt me anytime you can when you cannot understand my explanation. So let me just draw a magnified version of this. Yes, I will just try to magnify the version without any. So this is a part of your V out and V in graphs, and let's say that this point is corresponding to what? Corresponding to your V in DC, comma V out DC. Okay, so when you have no input at all, no small signal input, then your output will be once again V out DC. However, if you add a small V in, then you will have a small V out. Then how large is it? That is my question. So think about this one. Yes, I added here. This is in DC, and I just introduce a small change. So how small is it? So let me just call it as 1 millivolt. So I just introduce 1 millivolt increase. Then we should be able to answer yes. Previously the point was here, and when we increase our input voltage by 1 millivolt, of course our operating point or our output voltage will be changed to second point, and of course this difference is corresponding to what? Corresponding to our V out. Then how can you calculate this, the magnitude of your V out when we have just 1 millivolt? So that is not that difficult. Now you can understand this V out will be given by what? Your dV out and dV in. You know this quantity, and multiplied by the magnitude of your voltage excitation. What was it? Previously it was 1 millivolt. Yes, so when you have 1 millivolt excitation, and this 1 millivolt excitation will be copied into your V out difference with an amplification factor of dV out and dV in. So Now please think about this one. Instead of this 1 millivolt, let's just use a symbolic form like V in. And do you remember the relation between dV out and dV in? Yes, you remember it. V out is now given by minus R times your transconductance multiplied by V in. Still, I'm asking you, why do we have this behavior? Previously we had V out equal to VDD minus R times ID. So small change in our output voltage is directly related to minus R times delta ID. So that's the reason why our relation shown here can be obtained immediately. Okay, so now let's come back to our major purpose. We wanted to build an amplifier. So we wanted to maximize the amplitude of our output voltage. Let's keep its amplitude is fixed. Okay, that is fixed like 1 millivolt. And if we have better amplifier, maybe we have larger and larger amplitude of an output voltage. So then how can we maximize this V out? What will be your strategy to maximize the V out? Of course, from this expression, yes, we have a negative sign, but negative sign is understood. Of course, for given R, then we can try to find out maximum point for GM. If we are working with the maximum GM point, then we can maximize the amplitude of output signal. So why don't we introduce a certain quantity like gain? Gain is defined by V out over V in. Of course, please note that here we have a time signal and time signal in principle. So V out divided by V in doesn't make any sense. This expression should be regarded as like this: amplitude of V in and amplitude of V out. Okay, then we can have well-defined gain quantity, and our goal is to maximize the gain quantity. How can we increase the voltage gain? Then the gain is now given by what? Given by simply speaking, gain is given by minus R times GM. So if we have a higher GM value, then we will have a larger gain. Okay, so do you have any question about my explanation? So if you have any question, then please let me know. Or right now you don't have any question, but when you come back to your dormitory room and when you study by yourself, maybe you will have plenty of questions related to today's lecture content. Then please send me an email, or another way is please ask me to make an online office hour. Then I will open another online office hour to answer your additional questions. So please feel free to send me an email. Okay, so okay, I will just wait for 1 minute for your question about this concept. No, no question from students. Okay, then please have your time, and if you have any question, then is more than welcome to send me an email about your question. Okay, then let me just summarize the discussion up to now. From the curve of V in over V out as a function of V in, we have found that if we try to use it as an amplifier, and if we wanted to maximize the voltage gain, then we have to find out the maximum GM point. And where can you find the maximum GM point? That is the property of certain transistor. Depending on the technology, we have different optimal point. So please have your own data sheet, and you will find that the optimal point for your application. So if you just understood all of the contents up to now, maybe you have certain, not very clear, but certain feelings like this. So now we can think about this situation. Now we have a certain R value. Of course, this R can be set by a designer. As a designer, you can select the value of R, and also you have a resistor here. So yes, and also as a designer, you can select what you cannot select, for example, TOX. No, this is not possible in general. What you can select is the geometric factor open to the designer. So typically what you can do is you can select W and L. Then obviously the quantities you cannot change it is like this. Mu n, okay, this is a given, and Cox, okay, that is given. And how about threshold voltage? Threshold voltage is also given. So as a designer, what you can change is usually W and L. However, there is another thing you can select, although not W, not L, but you can select another important quantity. What is the another important quantity? You can select VGS, it's a DC quantity, and also you can change it VDS, and it's a DC quantity. So changing the relative ratio of your W, L, and R, then you can find out the optimal operating point for your gate voltage and drain voltage. Since you are a circuit designer, it's up to you. You can change your W, L, and R value, and by changing them, you can change the performance of your circuit. Okay, so I think that is the best case, best understanding up to now. You feel that okay, maybe here we have input signal, and here we have output signal, and yes, if we change this small voltage here, then the output will be amplified and we will have a larger amplitude as an result of this amplification. That I guess that is the best understanding of Fourier. Okay, so do you have any question, or if you cannot understand my explanation about this last part, so please let me know. Then I will repeat this part again. Okay, so what point is this understanding is not enough to really make the working circuit. Or for example, let's assume VDD in this case happen to be, for example, 1.8 volt, for example, and let's say that your optimal value for your gate source voltage is happen to be, for example, let's say 0.9 volt. That is just an assumption, so value is not that much relevant. But anyway, let's assume this one. Then, from our discussion, if this is just corresponding to 0.9 volt, then what we can expect is, first of all, we have to apply our gate like this way. Apply first 0.9 volt, also add one input signal. So from now on, let's discuss about how can we apply 0.9 volt to our gate and also V in into our gate terminal. So obviously, when I say so, 0.9 volt, your first reaction would be like this. Okay, since gate voltage should be 0.9, why don't you just add 0.9 volt to this gate terminal? Yes, that will be the perfect way. However, please note that this is your circuit, and who generate 0.9 volt for you? 0.9 volt is not available. So you know that two available voltage is of course ground. Yes, that is always available, and VDD, that is available. So in your circuit, you can select 0 and VDD. Then another way is, please let's try to ask higher rank engineer and visit your boss, and oh, I need 0.9 volt, so please make another line where that line is maintained as 0.9 volt. That is no way. Nobody can generate such an intermediate voltage for you. So you have to generate a certain voltage required for your design. Then how can you generate certain voltage which is desirable for your circuit? For example, if this is 0.9 is your desired voltage, then you know this is yes, VDD and ground. Then you can introduce another R and another R. Let's call it as this is R1 and R2. Then let's think about what will happen to this system. Oh, now this system becomes much more complicated than before. However, please think about the journey of electrons. Okay, this is highly biased and this is lowly biased. So we can think about current path from VDD to ground. Then what will happen? Okay, obviously there can be a path for electron current. Okay, so we can have the path from VDD to gate voltage gate terminal through V1. After that, also we can have a direct path to the ground. Of course, a student can ask me another possibility. Instead of directly move from VDD to ground, we just stop here and try to follow into the gate. However, please note that this is MOSFET, and what is it? What is this point? Yes, we have a perfect insulator. So if we are working at low frequencies, actually gate current is always assumed to be negligible. So although we have possible two passes, one from gate to ground through R2 and another path is from gate terminal to the ground through our gate oxide. However, this second possibility is not effective at all. So we have just one single current path. Then now we can think that this is actually corresponding to VDD and ground and serially connected R1 and R2. Okay, so now if we have really such a simple case, then voltage here can be represented by VDD multiplied by the overall resistance R1 plus R2, the overall resistance of equivalent resistance of two serially connected resistors, and R2. That can be a voltage for this point. For example, if you wanted to have just half VDD for this point, then if you wanted to have VDD as an gate voltage, then simply you can set your R1 and R2 equivalent. Then you will have just half VDD applied to your gate voltage. Then think about another case. Instead of this 0.9, you have to have 0.6. In this case, if you have R2 and happen to be R1, for example, here you have R1 and happen to be R2 becomes, oh, sorry about that. So here you have R2 and R1 becomes 2 times R2. Then obviously you will have R2 and R1 is 2 times R2. So you will have just 1/3 of VDD for your gate terminal. So are you with me? Simply speaking, now you understand. In order to use your simple circuit which has an MOSFET and a resistor as an amplifier, you have to find out the optimal input voltage. So gate voltage should be biased to the optimal value, and obviously this optimal value cannot be either, you know, VDD. You have to generate an intermediate value between 0 and VDD, and that voltage is not directly available to you. So first of all, in order to provide the DC bias voltage, you have to introduce additional circuitry to build this DC voltage. So now you have certain voltage corresponding to the R2 and R1 ratio. So do you have any question up to now? Then obviously I wanted to wrap up today's lecture with my final comment. Okay, now it looks beautiful. For example, we can find out any bias voltage for this circuit. Now, at least in a DC sense, for example, our gate voltage becomes just VDD multiplied by R1, R2, R2. Yes, by selecting proper ratio between R2 and R1, we can select VG. But point is, if you introduce such kind of serially connected resistors between VDD and ground, so think about the power. What will happen? Yes, certainly you will have the current flowing through in this way. So continuously it will consume certain power. Of course, the power will be given by this way. The power is given by the product between voltage difference and current. Voltage difference between VDD and ground is obviously VDD. And what is the current? Current is given by VDD divided by an equivalent resistance R1 plus R2. So that will be the power consumption only by the biasing circuit in order to provide our in order to set our circuit in a right position for amplifier, we have to spend our DC power. Otherwise, we cannot have any amplification. That is one thing you have to keep in mind. There is nothing given at free. So we are now spending our power to provide a certain circuit called amplifier, and it is consuming the power. Okay, so I think that is all for lecture 20, and now we are prepared to provide additional small signal input on it. So that will be discussed on Wednesday lecture 21st. So if you have any further question, then please send me an email, then I will happily answer to your question. Okay, thank you for coming, and see you Wednesday. Bye.